Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Welcome to guest lecture series on SDGs today, Tuesday, 19 January 2021. My name is Samara from ITS Global Engagement and will be your master of ceremony this afternoon. Thank you for joining our guest lectures on SDGs. Before we start our agenda, let me inform you of some rules of the event. First, adjust your name into the format name underscore campus. Second, turn on. Please always turn off your microphone and only turn on the microphone when the moderator gives the chance. Third, please turn on your camera. Fourth, adjust the seat position comfortably and prevent the backlight effect. Fifth, ensure your network has a stable internet connection. Sixth, please fill up your attendance at bit.ly/attendance underscore GLS SDGs. Our committee will also send the attendance link in the Zoom chat room. 7. Participants who wish to ask questions during the question and answer session, please send your question into intip.in/Q&A GLS SDGs, and the link for question will be also listed in the chat room as well. Or you can ask directly by clicking the raise hand picture. Ladies and gentlemen, today's guest lecture series theme is Electrochemical Energy Conversion System Utilizing Bio-Related Catalysis, which will be delivered by our speaker, Professor Masato Tominaga from Saga University, Japan, and this lecture will be moderated by Dr. Raden Darmawan from ITS. Before we start our agenda, allow me to deliver our schedule today as follows. First is the opening, that will be proceed by introduction to moderator and speakers. Next, we will be followed by lecture session by Professor Tominaga. Fourth is the Q&A session, will be followed by certificate awarding. And last but not least is the closing. Now, before we proceed to our next agenda, let me introduce our moderator today. Our moderator is Doctor of Engineering Raden Darmawan, lecturer in Department of Chemical Engineering ITS. And as for his educational background, he received his doctoral degree in Kumamoto University, Japan, his master and bachelor degree in Institut Teknologi 10 November, Indonesia. He is also involved in some professional organizations such as the Society of Chemical Engineering, Japan, or SCEJ, as regional associate in foreign countries since 2020, and Indonesian Engineering Association, PII, since 2017, and also the Society for Biotechnology Japan, or SBG, in 2013. And his expertise or research interest is in biotechnology. Now, without further ado, let us proceed to the main agenda. To Dr. Darmawan, the time is yours. Hello, Dr. Darmawan.
Okay, thank you. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Miss Samara, can you help me ask about the CV Professor Masato Tominaga? Okay. Hello everyone, good afternoon. First, I would like to thanks to Ms. Samara for introducing me. First, I would like to introduce for our speaker. Here, I'm Darmawan. I will be a moderator in Professor Masato Tominaga obtained a doctor, master, and bachelor degree in Kumamoto University, Japan, about the organization experience, There are a lot of organization experience from 2020 until now as a representative the Japan Society of Analytical Chemistry and 2019 until present head of Department of Chemistry and Applied Chemistry in Saga University, Japan. And 2018 until 2019, International Advisory Board, the 18th International Conference on Quality in Research, and 2017 until present, board member Kyushu Division of the Japan, 2017 and present, board member Kyushu Division of Electrochemical Society of Japan. Okay, to shorten the time, I invite you, Professor Masato Tominaga, to start your presentation. Time is yours, please.
Okay, thank you very much, Dr. Ramon, for your kind introduction. So I would like to start my slide. My slide is okay. Can you see my slide?
Yes,
Yes,
Professor.
Professor.
Yes, okay. So, okay, so ladies and gentlemen, Selamat Japan. So first of all, I would like to give my great thanks to all of the members of this guest lecture series, especially Dr. Dharmawan as the moderator, and the Rainy teacher, Rainy Sensei, and Oin Sensei. I'm very honored to be here as a presenter of this guest lecture. So, and if you are interested in my talk and research, please join my laboratory homepage. I also prepared in Bahasa, Indonesia. So I think nobody knows Saga City in Japan. So I would like to introduce briefly Saga City and myself. So almost people are staying Surabaya, ITS here. So this is Japan. There are 4 main islands: Hokkaido Island, Honshu Island, and Shikoku Island, and Kyushu Island. Saga City is located in south part of Japan in Kyushu Island. So Fukuoka is the largest city in this Kyushu Island. So you know Tokyo here, and Kyoto, Osaka, Nagoya is here, and the Saga is here. So Saga is located in countryside, city side, so not so crowded. So you can focus your research, study, and everything. No crowded and not so many COVID-infected people. You can enjoy the beautiful nature and traditional building and some eating, and yeah. If you have a chance, please visit my city, Saga City. So, and then I would like introduce myself a little bit. So my first visiting ITS Surabaya was 2013. So I was here, looks like very young. I want to become like that. So, and then he is a Professor Fansuri, chemistry department. She graduated, she finished already, she already finished her master degree, and she is working in the ITK, and also, yeah, there are some memorial people. And then I'm third visiting was in 2018. I had an international seminar at the chemical engineering department. Dr. Dharmawan was here, and I'm very enjoyed. Professor Freddy was there. This is seventh visiting ITS 2019. I discussed with the MOU with the rector of ITS. So my last visiting, eighth visiting ITS was last year, 2020, January, before pandemic of COVID. Yeah, Dr. Freddy was there, and Dr. Dharmawan-san, Dr. Dharmawan, and I was here. So this is, so I want to again visit the ITS. So maybe in this year, maybe next year. But anyway, my first visiting overseas place should be Surabaya. So I have mainly 4 projects. So one is the bioelectrochemistry using carbon nanotube and the enzyme. Second one is microbiofuel cell. This is collaborated with Japanese company. Third one is a tantal condenser using a polypyrrole. This project is collaborated with Panasonic. And the last one is I use the nanoparticle to develop sensor, chemical sensor, and the catalyst for reduction of CO2. Well, so why electrochemistry? This electrochemistry can contribute energy conversion between chemical energy, electrical energy. So electrochemistry is very important field. So we can calculate using this equation gives energy equal electron transfer number, Faraday constant, and voltage. This is electrical energy. So there are many electrochemical conversion systems. For example, battery chemical energy convert to electrical energy, as you know well. Also, fuel cell is like this. Even in our body to generate energy. So in our body, there is some chemical reaction, and this reaction, next reaction is electron transfer reaction, especially in our membrane of mitochondria in our cell. And then finally, this energy changes to chemical reaction to generate ATP from ADP. So this electrochemistry is very important to develop sustainable development goals. As you know, SDGs, electrochemistry can contribute much on the SDGs. Okay, today's my talk is like this, introduction of electrochemistry. So I would like to talk water electrolysis and hydrogen fuel cell. And second is main part, energy conversion utilizing bio-related catalysis, using enzyme, using microorganisms. The first topic, electrochemists use electrode like this metal electrode. Sometimes we use carbon electrode. So there are many types, plate type, a wire type, needle type, and the spring type. These are electrode. And then we move to water electrolysis. This is overview of water electrolysis. Maybe you think about, oh no, I understand water electrolysis. I learned water electrolysis in junior high school or high school. But water electrolysis is very important to understand electrochemistry. So I chose this topic. So there are two electrodes in the electrolyte, right? And two electrodes connect with a DC power supply, direct current power supply. So what is electrolysis? Use electrical energy to promote oxidation or reduction reactions that do not process naturally, right? And then electrode is the electron conductor. So in this case, we use direct current. So it means this circuit must be closed between these electrodes. Yeah, this side connect each other, but open this side. But in the electrolyte, there are many ion conductors, anion and cation. So we can keep electric conductivity between these electrodes. And I use current density. The current density means like this: current number per square centimeter, because current current value is depend on the electrode surface. So sometimes, many times we use like these units. So last year, Toyota developed the new Mirai. Mirai means future in Japan, in Japanese. So anyway, this is not just car. This motor driven by hydrogen fuel cell. So the system is like this. So this car has a hydrogen tank, and then this hydrogen is produced to the fuel cell. Also, oxygen is produced from air. And then in the fuel cell, electric power is generated and then this energy is used for motor, right? So again, hydrogen and oxygen is react in the fuel cell, and then water is generated. During this reaction, we can get energy. But important point is how to make a hydrogen. Okay. So we can make hydrogen by using water electrolysis. Of course, we need the energy injection. So maybe we can use solar panel or another sustainable energy. So I want to, I hope you understand facts of water electrolysis. Okay. First one is from pure water to aqueous water, everything can be decomposed into hydrogen and oxygen. Even though you use very pure water solution, we can decompose into oxygen and hydrogen. Second point is water cannot decompose at voltage lower than 1.3 volt. Okay. And third, the electrolysis behavior is strongly depends on the water solution. So this is a graph, a figure, the voltage and current density, and this is curve for H2SO4. This is curve for tap water. This straight line curve, this straight line is for pure water containing CO2, and this line is for pure water not containing CO2, containing H2. Of course, we need to more than 1.23 volt is required to make water electrolysis. And then if you want to obtain this current density, so the applied potential is quite different. For example, in the case of H2SO4, we applied only 2 volts to make a water electrolysis. But in the tap water case, we need 4.5 volt. Moreover, when we use pure water containing CO2, more than 200 volt is required. And then, pure water containing H2O is required much higher voltage. And then the current density versus voltage, this behavior is strongly depends on the solution type, like this. Yeah, the curve and the straight. So quadratic curve type is H2SO4 and tap water. Straight line type, pure water. While like this behavior depends on the later determining. So in this case, later determining is electron transfer reaction. The other case is later determining is electrophoretic. So this water electrolysis behavior different each other. Okay. So let's think about reaction at anode and cathode. Maybe you don't know anode and cathode. If you do not cathode and anode, please memorize in this time. So cathode is electrode side, where reaction occurs. So in the case of water electrolysis, hydrogen ion reduced to hydrogen gas. The anode is electrode side where oxidation reaction occurs. So like this reaction is occurred at the anode side. So overall reaction is like this. Should be you know where. And then standard enthalpy of gives energy. Maybe student of chemical engineering and the chemistry department, that student can be calculate. This gives energy change. So this number is a standard enthalpy of gives energy. You can find this number at the end of your text, at the end of your textbook, physical chemistry textbook. So I would like to give you small quiz. What is the energy required for water electrolysis? Gives energy. So overall reaction is like this, and gives energy is like this. So what is the gives energy required for water electrolysis? So I wait a few minutes for your answer. Please calculate yourself. Very easy. You did? You need more time? I think ITS students are excellent, so should be finished. Okay, I would like to move to next. So delta G can be calculated like this. So energy changes like this. When you obtain this energy change, you can calculate voltage to make electrolysis using this equation, right? So delta Z you obtained already, but in this case we use kilojoule per mole. So we need to transfer joule and electron transfer number. So in this case 4, n equal 4, and Faraday constant. And then finally we obtained 1.229 volt, almost 1.23 volt. So theoretically, this voltage is required to make water electrolysis. Where? So water molecule is very, very stable compound. is it? But we can decompose water molecule only 1.23 volt. You have some battery, right? That battery voltage is around 1.5 volt. Only you can make water electrolysis using just the battery, theoretically. So why we can decompose water molecule by using electrochemistry? Okay, and this is the figure. This is the electrode, anode electrode, and this is the cathode electrode. Okay, and this is potential range. So, in the case of water electrolysis, anode electrode is charged positively like this. To cancel this positive charge, an ion is moved to this at this surface. So this is like a condenser, right? Plus and minus. So we call this layer is electric double layer. Of course, also cathode side. Electric double layer is appeared like this. The important point is this thickness. This double layer thickness is around just only 1 nanometer, right? And let's think about this potential curve. Okay, this is bulk region. There is no voltage. I mean, there is no potential difference in the bulk solution. The potential is applied only this electric double layer region. So let's think about, so for example, in the case of 0.1 molar H2SO4, so each nanometer thickness, this thickness is about only 3 water molecules size. So this 1 volt is applied only 1 nanometer. This is equal like this. So huge voltage per centimeter. 1 million, 10 million volt per centimeter. So this is huge energy. So at this small area, the huge energy is applied. So we can decompose water molecule. That's a reason, but very safety, right? Okay, we move to our next topic, energy conversion. So maybe you are a little bit tired. So 3 years ago, 2018, I had a great time in Padang. I attended the international seminar, international conference organized by ITS and Universitas Bun-Hatta. So I really enjoyed the conference. Also, I really enjoyed sightseeing. Yeah, Dr. Darmawan accompanied me for sightseeing. And I really enjoyed marine sports, jet ski. It is me and Dr. Ramon here. And then I moved to the ITS, of course. I had a seminar at the chemical engineering department. And then also I discussed with MOU. I discussed MOU with the vice rector. Yeah, this is a famous place, you know. And this is very, very nice memorial for me. Well, I go back to real. Well, I said electrochemistry contribute energy conversion between chemical energy and electrical energy. But we need a catalyst to reduce the active energy. So what kind of catalyst do you think? Maybe you think a metal, right? For example, gold, platinum, palladium, something like that. So long ago, I synthesized like these nanoparticles. Diameter is 1, 3 nanometer, 5, and 2. As you know, gold is like this, right? Gold color. What is this color? Diameter is 13. This nanoparticle color is gold, or another color. The answer is the pink or red. How about 5 nanometer? 5 nanometer color is pink, like 13 nanometer size. No, this color is purple, like a black. How about 2 nanometer? This color is black. But anyway, so this color is depends on the size. And then so why we synthesize like these nanoparticles? Also, a nanoparticle is used for a catalyst. So why? So a very important point is the cost. The reason is the cost. So because reaction is occurs at the surface of the catalyst, right? So surface area is important. And think about the gold film. The thickness is 1 micrometer. If you obtained 1 square meter using this thickness gold, the cost is like this. This is Japanese yen. At the time, price is like this. So now the price is twice, 2,000 Japanese yen per gram. So when used to 20 nanometer gold nanoparticles, cost is like this. And then you use 4 nanometer, cost is like this. But surface on the surface 1 square meter. So if you prepare small nanoparticles, you can reduce the weight of metal to obtain the same surface area. That's the main reason why we use nanoparticles. Okay, I prepared using gold nanoparticles to make a glucose fuel cell. So I modified, I prepared the gold nanoparticle modified carbon ferrite. This is a catalyst to oxidize glucose. Okay. This is a demonstration. This is we prepared the fuel cell, glucose fuel cell. So student inject glucose solution, alkaline solution. So yeah, motor is driven by this fuel cell. In your body, we have enzyme, right? Enzyme is also catalyst. For example, this is glucose oxidase. This enzyme reduced oxygen, catalytically reduce oxygen to H2O2. Also, this enzyme catalytically oxidize glucose. This reaction is coupled each other. Yeah, almost this enzyme is composed from amino acid. Amino acid is not electrical conductive material, but this enzyme has like this compound. This is FAD, flavin adenine dinucleotide. This compound can react with electron and hydrogen. So this compound shows like this redox reaction. So this enzyme has like this FAD. So this enzyme reduces oxygen. This enzyme oxidizes glucose. Some enzyme also have another metallic metal atom. For example, this is bilirubin oxidase. This enzyme oxidize bilirubin. Also, this enzyme reduces oxygen. This enzyme has 4 copper atoms. This is the redox center to make like this reaction. And then this is enzyme is catalyst, so we can prepare fuel cell using enzyme as a catalyst. So this is anode. The surface is modified with enzyme. This enzyme oxidizes fuel substrate such as sugar and alcohol. The other side, the cathode side, the surface is modified with enzyme. This enzyme reduced oxygen. So there is anode and cathode in this system. So I prepared like this fuel cell, fructose fuel cell. So this is anode. I modified fructose dehydrogenase at this electrode surface. So this enzyme oxidizes fructose. This is the oxidation reaction. It means this electron take an electron from the fructose. And then this electron move to the another side, the cathode side. At this surface, a lactase is modified. So lactase reduced oxygen using this electron and generate water. I would like to show you this fuel cell. This is carbon electrode. The surface modifies these enzymes. This is the fructose solution. So like this. So we can make electricity by using this fuel cell. Enzyme is catalyst in this system. And then we prepared like this very thin, small, wearable type electrode by using cellulose nanofiber. So cellulose nanofiber is green materials and lightweight. The problem is no conductivity, right? So I used nanocarbon to produce the conductivity. And we develop like this film. And also there are, this film has anode and cathode, and the both surfaces are modified with enzyme, glucose oxidase and lactase, and we obtained like this electric curve. The power density is not so high, but we obtained around 25 microwatt per square centimeter. This is very small electric power, but enough to operate energy harvesting IC chip. This energy density is enough to operate such a special IC chip. In the future, I would like to develop like this wearable fuel cell. Also, I developed like this wearable sensor, glucose sensor, and another sensor. Yeah, this is my dream. Okay, so I talk metal catalyst and the enzyme catalyst. Yeah, these are very nice catalysts. That's a problem. There are some problems. So gold, platinum, palladium, such some special metal, so expensive. The enzyme is very nice catalyst, but price is expensive, and enzyme can be denatured, broken soon, not stable, unstable. So let's think about microorganisms. So this microorganism has a lot of enzyme. This microorganism has many type of enzyme in their body, right? So I think this microorganism is enzyme package. And the important point is this is free except of some special microorganism, but usually free. We can take any type of microorganism from the ground, the sea sediment, the wastewater. So you know microorganism categories. For example, aerobic microorganisms and anaerobic microorganisms. Important point is this category focus on oxygen. right? But another category is like this. We can also consider categories. Focus on electron transfer reaction. So let me show you. The first type is this microorganism take electron from the metal or conductive material. And then this electron used for reduction of oxygen. This microorganism is related to the corrosion. This microorganism promote corrosion to take electron from the iron. So another type is this microorganism give electron to the electrode, conductive material, and metal. Okay, this electron come from the organic compound, oxidation reaction. So we use this microorganism for microbiofuel cell. But an important point, this microorganism is required anaerobic condition. Anaerobic condition. Okay. Otherwise, this microorganism is not worked well. So this is a cartoon of our microbiofuel cell. We use anode and cathode, of course, and anode is set under the mat. Cathode is set close to the surface because the cathode requires oxygen. So important point, aerobic in the mat, already anaerobic condition, right? So there are many advantage using a mat because this is just very simple structure. We cannot use, we do not use some special cavity to protect the oxygen. No, inside the mat is aerobic condition already. So we do not some cavity size. So there is no high cost because the cost is only anode and the cathode, the electrode. And the easy operation, also, of course, free bacteria. I would like to show you my demonstration. This mud from sea sediment. And this is the carbon ferrite electrode. The size is 10 by 10 centimeter. This is cathode. The anode was set under the this sea sediment. So motor is like this motor. We did not use any catalyst except of microorganisms. Yes. So not limited in this system. We visited Surabaya, Salamad Bridge, 2014. At the time, Dr. Ramon was a student, Dr. Ko student, a long time ago. And then we set our system under this bridge, Salamad Bridge. Also, we tried Rapindu MAD 2015. And then we obtained we obtained the electrical power even in the Rapindu MAD. Of course, sea sediment near Slamad Bridge like this. So last August, I tried at the field of paddy field. So we set like this MFC cell set in the paddy field, and then we obtained like this electric power. So there are 6 cells, and maximum power is 450 millivolt, and the current is around 3.5 milliampere. In the future, I want to use this electric power to operate field sensor. And this some newspaper pick up this research result. Also, broadcast pick up this research. This is NHK is very famous broadcast in Japan. So this is the conclusion. Electrochemistry is very important in the energy conversion between chemical and electrical energy. And so electrochemistry can contribute on SDGs. This is acknowledgement. This is a company. This is a JST, Japan Science and Technology Agency. This is a JSPS, and next, and my university. So finally, I would like to announce something. So this is alumnus who invited my laboratory as a Sakura Science student. So first student from ITS in 2015. And many students of ITS, many ITS students visited my laboratory. Yeah, but I could not invite any student last year, of course, because of COVID. So in this year, I would like to invite from ITS. Next year, depends on the condition of COVID. Okay, I would like to finish my talk. Thank you very much for your kind attention. Terima kasih. Thank you very much.
Okay, thank you so much for your valuable lecture, Sensei, Professor Tominaga. Before opening the discussion, let me summarize about the lecture. The title, Electrochemical Energy Conversion System Utilizing Bio-Related Catalysis. From the lecture divided into two parts. First, about the water electrolysis and hydrogen fuel cell, and second part about the energy conversion utilizing bio-related catalysis such as enzyme and microbes. From the first material, Professor Masato Tominaga explained that there are many shapes, types electrodes can be used, such as gold and carbon electrodes. Then overview about the water electrolysis, from how the water electrolysis work to the application or implementation. And about from the second part of this presentation, it is described that energy generation can be yield from organic material such as glucose, fructose, and mud. and also using enzyme and microorganisms such as in the system like the glucose fuel cell, enzyme catalytic fuel cell, fructose fuel cell until microbial fuel cell.
Mm.
In addition, another part also in the lecture is shown about the CNF, cellulose nanofiber, based thin electrode can be used in the fuel cell system with in the fuel cell system. And the last one about the electrochemistry is one of thing has an important role for SDGs, especially for energy generation for future. I think this is about the lecture about from Professor Masato Tominaga. Now we are entering the discussion and question session. In here, there are two types. You can type using the link, yeah, mentioned in chat room. Yeah, you can type your question in the link, or you call raise your hand and directly you uh, please mention your name and your institution, please. Is there any question or comment from audience, from participant, please? Okay, Sensei, waiting from others, let me ask you. I have a small question. I'm
Yes.
wondering about what should be considered when we before running, yeah, before running the microbiofuel cell, like
Yeah.
in your last part presentation slide, you shown about the application of microbiofuel cell in the especially in the paddy field.
So your question is how to use
Consideration,
consideration
yeah, consideration,
the biofuel
yeah, before running, before
running.
running, yeah.
So mm, in the it's very difficult. I know. We just start development of paddy field microbiofuel cell. So there are so many problems to continue the operation. So because the microbiofuel cell required water, right?
Yeah, yeah.
Yeah. So at first we select the paddy field because the paddy field has a water, but not. Mm. And the other problem is conductivity, electrical conductivity between anode and the cathode. Before we use sea sediment, in that case, the sea water is very nice conductivity. But in the paddy field, water is not so much contained anion and cation ion. It means low conductivity. So we separate the distance of anode and cathode is very important, right? So when we select a long distance between anode and cathode, it means the high resistance is occurred between anode and cathode. But we close to the anode and cathode, so anode must be keep anaerobic condition. But cathode requires oxygen. So important point, all of oxygen react at the surface of cathode side to protect leak the anode side. So there are many important points, and also still we are developing this system.
Okay,
And
how
then,
about
please.
okay? How about the person from fertilizer, Sensei? Fertilizer,
Fertilizer.
yeah, will support the system or not? Yeah, as we know, yeah,
After
fertilizer,
this process.
yeah, the microbial fuel cell process.
Yeah,
The
I think that's a good idea. Yeah. So there are many type microorganisms, right? So I think Rapindu mat is strong acid, right?
yeah.
So usually biomass wastewater is the acid solution sometimes. So right, such a microorganism is very nice to such a so microorganism in the Rapindu can be used for anode catalyst to reduce the BOD, the biomass wastewater. After that, you can use fertilizer, or during this system, maybe finally we obtain the fertilizer. I'm not sure, but yeah,
Okay.
we can connect.
Yeah. Thank you, Professor. Okay, I will try to read in the Google form. And there are some person
How to extract the matter.
question. Yes. First from Intan Dewi Pinasti from ITS Department Chemistry about the question in fructose fuel cell, can fructose replace with sucrose? This is
Yes,
the
of
question
course. Yes.
from Intan Dewi Pinasti.
Yeah, it is possible. It depends on the enzyme. Yeah, we can select any type of enzyme, right?
Yeah.
So it means we can select any type of catalyst. We change the enzyme, we can change fuel. We can change we can use any fuel if we change the enzyme.
Okay, thank you, Sensei.
Yeah, you're welcome.
Second question. This is from Citra Dewi Rahmania from ITS Department of Chemical Engineering. The question: is it possible to determine the exact reaction which happened in Microbiofuel cell through its electricity output?
Sorry, Dr. Tarman.
Okay.
I couldn't catch well.
Yeah. Is it possible to determine the exact reaction?
Exact reaction.
Yeah, exact reaction which happen. Which happen in Microbiofuel cell.
That's a good question. I want to know.
Maybe Citra, can you
maybe her question is
directly
about what kind of microorganisms, right?
Yeah. Yes,
maybe
Sensei.
I can analyze, but I did not do. I did not. Maybe Geobacter, maybe Schwannera.
Yeah.
I'm not sure now. But in my policy, I don't care about. I can get the electric power. That's enough for me.
Yeah. Depend on the microbial community, right?
Yeah.
Sensei.
Yeah. But we can analyze using 16R RNA system.
Yeah.
But it takes a cost. It takes time. Yeah.
We should know about the microbial community analysis first.
Yeah.
Later
Dr.
we
Ramon,
can
you
check.
Can do that. You can do that. I need your help.
Again, Sensei,
Yes.
in here from Nihaturoma. Sir, how to extract mud as electrode? I mean as the square shape. From the chat room, Sensei. From
Yeah.
the chat room.
How to extract mud as electron? What? But I cannot understand that means. Extract mud.
Yeah.
So we use just mud. I did not any treatment.
Okay, maybe Nihatur Rohma, can you
Okay,
directly ask to Professor Masato?
okay, I will try.
Thank you for your kind attention. Thank you
Yeah.
for your question.
Yeah, because I confused. You already mentioned the mud is a contact microorganism that can be used as electrolyte or electrode. Like you show us the square shape, but how it not like contaminate with the water or something? How to make it like metal or metal electrode? Because it's different.
Okay. Yeah, I understand your question. Thank you for your question. So the problem is cathode. So because as you mentioned, cathode is contaminated by microorganisms to operate long time. So we can use some metallic nanoparticle to make a cathode. We use just carbon felt electrode. Even though we use carbon felt electrode, the surface is contaminated, covered with biofilm for long time period. So that one is very important. We need to develop, revise such a behavior, but I don't have nice solution to do that. So my answer is okay for you.
Yes, okay.
So another you have another question?
I know, just confused how to use that make microorganisms because we usually use like metal, like ferro, nickel, and the other chemical materials. But for like glucose, fructose, and
Yes.
microorganism is new for me.
Yeah. So your question is why I use the microorganism, right?
Yes,
Yes. This is just one possibility. Yeah, we can use nanoparticles. We can use enzyme. We can use microorganisms as a catalyst. So we can use many type catalysts. So which depends on the situation.
yes, very nice.
Yeah. So
And it's very cheap compared the price
yeah.
of another particle. I get it.
Yes, yeah. But microorganism is free. That's one also very important. So
Yes,
everybody can be used, right? So
yeah.
enzyme is So enzyme is very expensive, right? And not stable.
Okay. Thank you, Professor.
Yeah, you're welcome. Thank you for your question.
Okay, Sensei. We go to the next question.
Yes.
The question from Marsanda Febriana from ITS Department Electrical Engineering. This is from Electrical Engineering Department. The question is, how efficient an electrochemical energy to become a renewable energy resource?
please say again.
How efficient an
Efficient.
electrochemical energy
How
to become a
efficiency?
renewable energy resource.
Efficiency.
Efficiency, yes.
I see.
The point
Efficiency.
is efficiency.
I'm not sure. Depends on the system. Yeah, but very important point is fuel cells is not to depend on the size. So when we use some if we use we make electric power by using gas and gasoline, huge system is required because a large system is make a high efficiency. If we prepare the large system, the efficiency is higher than smaller one. In the case of usual electrical generation, but in the fuel cell, the efficiency is not depends on the size. Small, very small size, the large size, and the efficiency is almost constant, not to depend on the size. That's one is very important point in the fuel cell system. Dr.
Okay.
Darman, do you understand my answer?
Yes, Sensei. Yeah, yeah, Professor.
You understand, so thank you.
Okay. We have still time for discussion. Maybe is there any question again from audience? Please. You can raise your hand or type in the link, in the Google link form. Okay, Sensei.
Yes.
Another, I mean, I would like to know.
Yeah.
In Japan, have already applied the system. I mean, microbiofuel system have already applied in the Japan.
Applied
I mean, maybe
not yet.
Not yet. Still laboratory scale.
Some company developed the pilot plant, but not realized.
Oh, thank you.
Yeah, still pilot plant.
Okay.
The company use the wastewater from industry.
Why, Sensei?
Why?
Because of cost, high cost, or maybe the small electricity generation can be obtained.
Both. Yeah, high cost.
Yes, cost and also.
Yeah, also low efficiency.
Low efficiency. Okay.
Yeah, of course. As you know, anode side. Yeah, at first period is okay. So I mean the short time is okay, but long time. So biofilm, the surface, the anode surface covered biofilm, right? Maybe efficiency is decreased, and also cathode side, the surface is contaminated something. It make decrease efficiency, and we need to replace the anode and the cathode several times. It makes it. It means the cost is higher.
Yeah.
Yeah. And the efficiency not enough, and the cost is now high, still high. So not realized now.
Okay, thank you.
Thank you.
Professor Masato.
Thank you very much for your nice question.
Okay. From audience, is there any question or comment against, please? You could raise your hand, or you could type the question in the link, please.
Maybe enough.
Actually, there is one more question on from the Google form, Dr. Darmawan.
Okay.
Google form?
Oh, okay, Sensei. This
Yes.
is also from my laboratory
Yeah,
member.
yeah. Thank you for your contribution.
From Mr. Simpliste Dusabe, yeah, from Chemical Engineering Department, yeah, from my laboratory. This is from Rwanda. His country is Rwanda. The question is, in your current research, did you try double chamber microbiofuel cell? Someone who is planning to make microbiofuel cell, please, this is, can read again. The question very long. I'm sorry.
Really?
Because I repeat again about the question from Dusabe. In your current research, did you try double chamber microbial cell? Someone who is planning in your current research, did you try double chamber
Hello, Dr. Darmawan. It seems you have a trouble with your
microbiofuel
connection.
cell?
Dr. Darmawan, excuse me. It seems you have a
Okay.
trouble with your connection.
Okay, I'm sorry. I have to stop my video. Dusabe, Mr. Dusabe.
Hello.
Hello. Okay, maybe directly you can ask to Professor Masato Tominaga.
Okay. Thank you, Professor. I'm Simplista Dusabe, a student in chemical engineering. Yes. So my question is this. So I didn't catch where in your current research you used single chamber MFC or use double chamber MC. So I was
okay.
So and I was asking if someone is planning to make a related research in MFC, can you advise him to use a single or a double MFC? This was my question. Thank you.
Okay. I use the single cell MFC.
So I need a reason.
I use single cell. Single cell. My answer is single cell.
So why did you prefer single
because
cell?
Because simple. Because single cell is a simple structure, right? It means to can reduce the cost. So efficiency, my MFC efficiency is not high, low electric power. So cost is very important. If cost is high, nobody use. Cost is very cheap, so everybody maybe use. So because of cost, so I select single chamber cell. Is it okay for you? Thank you for your question.
It is okay, Prof. Thank you.
Thank you, Mr. Dusabe.
Thank you.
Yeah, Mr. Dusabe, my student in laboratory, Sensei.
Oh, you have a good student.
Is there any question or comment? Okay, from Bu Nihatur Rohmah, Bu Nihatur Rohmah. Okay, this is, sir, how to get chance to student exchange in your laboratory? As no, I'm alumni, but interest with your research. This is a question.
Question?
Question
Comment?
or not?
Oh,
About
okay.
a chance
How to get
for
chance?
student exchange. Yeah.
Okay, my question is please ask to Dr. Darmawan or Professor Freddy. Yeah, they yeah, Dr. Darmawan and Professor Freddy support to you how to get chance to visit my laboratory.
Maybe let me know about Ms. Nihato Rohma, your institution. What's your department? From chemistry?
From chemistry department.
Yeah, chemistry. Maybe you can contact Dr. Freddy.
Yeah, that's
Okay,
easier.
okay.
Right.
I think easier.
Yeah. So because
Master student or doctor student?
No, I am alumni.
Alumni.
Just
Oh,
graduate from.
alumni.
Yeah.
Bachelor. Alumni bachelor.
Yes, alumni bachelor.
Okay.
Hmm.
Thank you.
Welcome.
Thank you.
Okay. From Malaysia, Sensei.
From Malaysia.
Yeah, from Malaysia. Let me
But
read
she
from
already
middle.
finished the
Maybe,
bachelor, right?
yeah. Okay, from Melkael Delagra, yeah, from Melkael Delagra from Malaysia. Can you help me, Melkael Delagra? Maybe you can ask to Professor Masato Tominaga directly
Yes, please.
to make easy.
Yeah.
Mikael Delagra? Okay, maybe I will read the question, Sensei.
Yes.
Mikael Delagra from UNIKL MFI Department Automotive Engineering Department
ITS?
from Malaysia.
Malaysia, okay.
Malaysia.
Hmm.
From the slide earlier it mentioned that MIREI vehicle using hydrogen oxide.
Mhm.
The question is, sorry, I have to scroll first in the sheet. And this is a long question. One sheet not enough. One sheet not enough. Cell there. Okay. Does Japan already use pure hydrogen gas as alternative fuel for vehicle?
Are you talking about?
Yeah. What I mean by pure hydrogen is without any mixture, like what's like does.
Yes.
What like natural. I'm sorry. Okay, Sensei. I repeat again the question.
Yes,
From the
please.
from the slide earlier, it mentioned about the MIRI vehicle using hydrogens oxide.
I cannot understand the MI. What kind of mean?
Okay, maybe I copy paste in the chat room, Sensei, to
Yeah,
make
please. Okay.
clear.
Pure hydrogen gas as the
Yeah.
alternative fuel for vehicle. Yeah.
Does Japan already use pure hydrogen gas as alternative fuel for vehicle? What I mean by pure hydrogen is without any mixture like natural gas vehicle.
Yeah, we use pure hydrogen gas. but I don't know the hydrogen gas made from alternative fuel cell or not. I'm not sure. I mean, the pure hydrogen is without any mixture. Like, yes, pure hydrogen gas is required for the basic, because otherwise the if the fuel cell is contaminated by another impurity compound, so very high purity is required to operate a fuel cell. Is it okay?
Is it okay, Melkael Delagra?
So yeah, in Japan, very pure hydrogen gas is produced by company, but I don't know how to make it. I don't know which energy is used. I don't know, but very pure hydrogen gas is required to operate fuel cell of a motor vessel.
Okay, thank you, Sensei.
You're welcome, sama-sama.
Sama-sama. Actually, we have still a little bit time for discussion and question answer session. Maybe is there any question? Maybe last question, maybe. Okay, from Citra Dewi, also from my laboratory member. Okay, Citra, maybe you can directly ask to Professor Masato.
Thank you for another chance. I will ask about the microbial fuel cell. When I see the prototype of the microbial fuel cell, there is a compact of fuel cells in there. So I will ask. The first question is about is not any cathode. Is cathode and anode is placed on this prototype, or the second question is, when I read some others some papers, papers, they try to develop another type of microbial fuel cell by using the by place the anode below the paddy fields, below the root of the paddy, root of the rice plant. So what do you think about this research? Is it more efficient, or is it will be have a lower efficiency than the prototype you are using right now?
Okay, thank you. Thank you for a kind question. First question is replace. So your first question, we can replace the anode and the cathode, is it?
Yes. Is the cathode and anode placed on the same prototype in MSD?
Yeah. Yes.
Yeah.
Oh, okay. Yes, assembly type. So yeah, we can not replace the anode and the cathode.
Yes.
We can exchange. We can exchange cathode easily, but anode. Yeah, but we cannot anode.
Oh, we can change the anode because on the below the because anode
because anode is because anode is covered surface of a cell, but cathode is just put on the inside the cell, so we can replace easily cathode.
Okay.
Okay. And
the second question is about the another type
understand.
recent research I have been read. So I
Citra-san, I understand your question.
okay.
Okay. Yeah. My answer is my efficiency is almost same to the previous paper,
Oh,
or a little bit higher than previous paper. But I don't know the long time efficiency because we started from August and we finished October, because from August to October is the the party field had the water. Other season dry, surface is dry, so we did not set the MFC. So we just tried 2 months, very limited. So I don't know what's happened for a long time period. So we want to investigate it. Yeah, you can do that. In near future, maybe. Thank you, Sura-san. Thank you for your question.
Yeah. Okay. Thank you for this change.
Yeah, sama-sama.
Thank you, Citra and Professor Tominaga. Okay, before close the session, maybe is there any question again, or maybe enough? Okay, I will try.
I'm enough.
Enough. Okay, since I think enough, in the Google link also there is no question again. Okay, ladies and gentlemen, maybe we can close about our discussion, question answer session. And from me, if I have a mistake, please forgive me. Then we can close this discussion session. Then I return back to Master Semurani. Assalamualaikum warahmatullahi wabarakatuh.
Yes. Thank you very much, Professor Tominaga, for the excellent lecture today. And also thank you, Dr. Darmawan, for conducting this amazing session. Please give applause to our speaker and moderator by using the Zoom reaction feature. Furthermore, we would like to present a certificate awarding to both speaker and also moderator. First is the certificate of appreciation for Professor Masato Tominaga.
Thank you so much.
You're welcome, Professor. And next, we will also have certificate of appreciation to Dr. Darmawan.
Thank you.
Once again, thank you very much to Professor Masato Tominaga and Dr. Darmawan for your availability on today's guest lecture series. Before we end our lecture today, we would like to invite all participants, as well as the honorable speaker and moderator, to take a group photo. So to all participants, please open your camera so we can start our group photo.
Yes.
Maybe we will wait for a few minutes until everyone open their camera. Okay, here as we have 4 slides, so please keep your smile until we finish the photo session. Right now, I will count to 3. 1, 2, 3. And Moving on to the next slide. 1, 2, 3. Okay, now we have finished our group photo session. And then, for the participants, please fill the feedback form to the link bit.ly/feedback GLS that you can also see on the Zoom chat room. We want to remind you that the participant who will get the stamp is the participant who comes on time during this event until the end and also fill the feedback form. Finally, we have reached the end of today's guest lecture series, and we sincerely apologize for any mistakes we may have made in presenting as Masters of Ceremonies and Committee. Thank you very much to Professor Tominaga and Dr. Darmawan and all participants for the attention and cooperation. We will see you in the next guest lecture series on SDGs on Tuesday, 26 January 2021 with a title, Preparation of Separating Reagents for Metal Recovery and Removal, that will be delivered by our speaker, Professor Keisuke Oto from Saga University, Japan. Good afternoon. Thank you and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
Warahmatullahi wabarakatuh. Once again, thank you so much, Professor Tominaga. Thank you so much, Dr. Darmawan, for wonderful session for this afternoon.
Yeah. Thank
Yeah.
you. Thank you so much.
You're welcome,
You are all welcome.
Miss Reni.
Yeah.
I
And then,
enjoyed. I
so
really enjoyed.
yeah, so am I. I really enjoy your presentation for today.
Really? Really?
Yeah. Yeah. And then we hope we can see you again in another time in Indonesia, actually. Okay.
Yeah, yeah.
And then for the participant, thank you so much for your time for today, and allow me to end the session in 5, 4, 3, 2, 1. Thank you very much, everyone, and keep safe.